Hi, uh, welcome to my IBM Coursera Data Science Capstone project. I'm Kaushik Sen. I'm working as Senior Manager in Information Systems with Indian Oil Corporation Limited. So, my project is based on the most traded commodity in the world and which is of utmost importance to our industry. Of course, it is crude. Crude, as you know, is found under the ground, and it has to be first of all it has to be explored, and then it has to be extracted, and then it has to be brought to a refinery. Now, what goes on in this refinery is we sort of distill the product, and we find out and we extract many different products out of the single product. So these different products are called cuts of the crude. So what happens is when I take I say this product which first enters my refinery, I call this as a whole crude, and as you can see out here, this single whole crude has produced seven different cuts of product. I'm sorry. So the first cut out here, which is the lightest one, probably this will be the LPG, liquefied petroleum gas. The second cut probably will be petrol, and so on. So as a refiner, my interest will be to maximize the product which has the maximize the maximize the production of that cut which has the greatest market value. Now, how do I do that? My hands are tied in most of the cases because many of the times, the crude itself is a determinant of what cuts it will be producing. Like in this case, it is this particular crude is a particular type of crude called Basra, and it produces under these ideal conditions. It will produce these quantities of these volumes of finished product. However, I have a little room to play with. There are certain parameters that I can tweak in the refinery so that say I can control to certain extent, say 2 or 3% how much diesel will be produced vis-a-vis how much kerosene will be produced. What I mean to see is I can to a certain extent I can determine the boundaries of these different cuts. So now, how do I do that? How do I fix the parameters? I do this with my refining knowledge and by the knowledge of the constituent of this particular crude. So, like this list of the different properties of crude is known as a crude assay. So here, like in this particular crude assay, which has been published by ExxonMobil, I'm being able to see that there are some physical and chemical properties of this mixture which has been calculated. I'm only showing you a small part of it. There are about 1,000 or so properties that every crude has. So as a refiner, if you can give me all these 1,000 properties, then I will be able to tune my refinery to perfection so that I can optimize what quantity of vacuum gas oil I would find out that I can extract, what amount of diesel I can extract. All that will be under my control. The problem is that when I start the refining process, I do not have all the set of parameters. The determination of all these set of parameters requires a lot of time, and it becomes impractical. So most of the results are available to me after my refining process is over. So what happens is, in most of the time, I have not been able to optimize my parameters so that they give me the best output. So the problem is, will I be given? But there are certain parameters out here, like say API gravity, which basically indicates the density of the crude. Let us say the sulfur content. Let us say the viscosity. Viscosity means how bad is the crude at flowing, something like that. A very informal definition. So these kind of things can be determined very easily right upfront. Now, will I be able to predict all the different other parameters of the crude from only a subset of parameters? That is a problem out here. So I will be given only those parameters which will be available from a quick lab test, and I will be having to predict all the remaining parameters of the crude based on this subset of parameters. So that is a question out here. So let us see how we proceed with this. And obviously, if I am able to predict this, then it will have a lot of impact in the industry. So these are the subset of the products that I was saying. These are some 10 attributes which are readily available to me, and this will be acting as my predictors. These includes API, which is a measure of density. Sorry, nitrogen. The nitrogen, obviously, nitrogen content of the crude. The pour point basically indicates at what temperature does a crude starts to flow, and all these different chemical factors. So now let us see how we went about with this problem. So um, first of all, this crude data is published by ExxonMobil at the beginning of every year, and as a subscriber, we have a database. We receive a database from them in the form of an access file, and which has got certain tables. And like let us say, four tables are of importance for this project. One is a crude master table having the crude region and all. Second is there is a map. There is an identifier in crude master which is crude ID and dataset ID, and it project crudes performs a mapping between these two. Then there is a set of properties, a list of properties, like I was saying, some thousand properties that was there. And WC data is the mapping of dataset ID, property ID, and value. And similarly, cut data has property of all the cuts. So when we start this project, I have this entire table as an access database. So unfortunately, I couldn't find a driver in Linux for this access database. So the first part of this ETL has been done using an R notebook in a Windows environment. And from the access table, I extract individual CSVs, and that becomes the starting point of my uh, Python and Watson notebook. So um, this running away. So a brief discussion on the architectural design decision. You can find the document attached in the project. So regarding the data source, we really didn't have much choice and didn't have much headache also, because it was offline data, and hence it was performance degradation during query was not a consideration. And in case and for enterprise data, what we did was we stored the partial results and the models as in IBM Cloud Storage itself, because of the low cost, high security, and other benefits. And for data integration, we have used Python 3.5 running on Jupyter Notebook on Apache Spark. This has been used obviously because of the high throughput, intuitive data handling, and SQL skill required, which were which is sort of available all through the organization. So for data repository, we have used Parkway file on IBM Cloud Storage. And for the discovery and exploration, sorry, we have used the Matplotlib libraries, and also an external library called Seaboard. Then finally, the models were run on SparkML, and we have ended the data product in the form of Jupyter Notebook itself. However, we have actually done this project also in R, and we have a finished product of this in Shiny as well. So now let us see the different parts of this. How we let us try to see the data pipeline. So the first step involves reading the data from. There were two sources of data because one file was quite large. I had to directly upload it to the object store, and another for the remaining other small files, I directly put it in the Linux environment. And I read both these data into the Spark data frame, and from there I made some feature selection, and there was a lengthy process of null removal, which I will show you in the notebook. And then there was then for the cut data, I had to do a denormalization because the individual properties was maintained in row format, and from there I had to make it to the column format. And these files, this completes the ETL part, and we then saved the data into a Parkway file. And on the Parkway file, then we performed visualization. And after visualization, we did one principal component analysis because the data was quite high dimensional. So we did a principal component analysis, and after that, the standard procedure of vectorization and normalization was used. One thing we have done here is we have taken the first two components of PCA, and we have used it as a engineered variable for the model. So now I would just like to show you the notebooks first here. This is my ETL notebook, and this is the visualization one. Let me open them simultaneously. Here, as you can see, first of all, I'm getting the data from the CSV file, and this is a cut data from I'm taking it from the Spark object store. So I'm reading the data into data frame, and now after that, here I'm making feature selection. I'm just putting some. I'm just keeping some of the columns, and then um, I'm joining this with the properties, the property column, and I'm keeping only those columns which qualify here. Like I had a set of 10 properties which I will be working with, which is here, and the data now looks like this. And then I am working with the this mapping file WC data, and here I'm trying to do a null removal. The dataset count here is 2682, but my I have got 11 property IDs including the weight. So as a result, the I should be getting 29502 rows, but I only got 29466 rows. Hence, 36 missing values were there. So what these 36 missing values had to be replaced with something. So what we did was, given a crude, we given a crude property which was missing, we went back to the dataset, and we went through all other records of that crude, and we replaced the null value with the average of all this record. This large for loop is doing that thing. And after that, after the end of it, most of my nulls were gone. Only about 7 or so remained. I replaced them with 0. Now, similar thing was done with the cut data, and after that, it was ultimately saved. So, um, that was it. And then now let us come back to the presentation. So then in the visualization part, We read the data back from the Parkway table. First of all, we wanted to find um, these are the different columns, and we tried to find the distribution of the data. We were taking one variable at a time, which was taking here as for example. Um, I was trying to see the Newt property, which is the tan number or the acidity measure of acidity of that of the particular crude. So instead of that, what we did was we converted this into, instead of seeing them individually, what we did was we converted the entire data into a binary data frame, and we ran a correlation matrix. Uh, so these are the different properties, and what I'm trying to see is how the individual properties of whole crude relate to themselves. So API, as you can see, has got more or less some or other kind of relationship with the other components. So nothing very striking out here. Uh, only API stands out, and probably Pore also has got. Pore has got very little correlation with anyone. So probably I don't know. In the principal component, probably Pore will be one major component. And these are the two viscosity figures. They are also having very low correlation among others. So now the same thing has been depicted instead of by numbers. Same thing we wanted to see with the help of XY charts, pairwise charts. So as you can see, this API, this it forms more or less a pattern with most of the other variables, apart from this probably with I don't know, pore, which was more or less independent, and these two quantities, viscosity at 77 Fahrenheit and viscosity at 104. These two properties are almost unchangeable. These do not contribute much to my dataset, to the variety in my dataset, is what we found here. So now, next, what we wanted to do was we made a data pipeline finally, and so that the entire thing is organized in a single place, and with a few lines of code, we were able to save that these entire proceedings into Parkway files, so that we can build models on that. And finally, uh, the model part. So in the model, we started with PCM. We found the individual components of the data, and the total variance explained by three. We assumed that we are going to have three component, and in fact, it worked very well. We found that with three components, about 99% of the data was explained, and these are the variances explained by the three components. As you can see, 72% and 24% are described by the first two component itself. The last component even is a little bit redundant. So we can as well remove that. We tried to find out the meaning of these factors, like as for example, the components entered in order is this. The first component, which explains 76% of variance, emphasizes most to, it gives the maximum weightage to asphaltene, and then to the tan number or acidity indicator, and negative emphasis on sulfur. The maths was all right, but probably the domain people could explain more why these correlations, these kind of things are coming, and why does it explain the variances so much. So finally, what we did was, on using these three properties, using these three components, we mapped the entire data set in 3 dimension, and this strange V sort of figure came out, and we removed the component because, as we saw earlier, the third component was really not interesting. The same, more or less the same pattern remained using only the two components. I am not very sure what to make out of this. Probably this is one cluster, and this is another cluster of data, and having uh, a bit of overlap in between them. So PCA was explaining the variance a lot. However, we found that using the first two components as a representative of the entire data, our model didn't run that well. So now we start to do that. We feature engineer and add the components of first two components of PCA as a predictor to my data, and this is where I assemble the first and second component element of the PCA, and there are some cuts of crude which are giving good results, but as for example this particular cut, the first cut itself is only r square is a mere 20%. So I can safely say that this doesn't work basically. I mean, taking the PCA component as feature variables didn't work in this case. So now we try to, in the second case, we tried to make the predictions based on the entire range of data, and that was more successful. And here, the same the level column is 4. I mean, the fourth, I'm trying to find out the fourth component, and for fourth component, the prediction is coming somewhere around 61%. So this is much better than what which we got through PCA. We tried to improve the model a bit more, and then we uh, we okay. What we did here was we tried to run this on the train data and test data, and we found the different results. And this is what has been the evaluation. Like the test R square was 65% compared to a poorer performance in case of training. So this is an okayish model, if you ask me, because the the worst I get is 55%. But let us see if we can improve further on this or not. So now I try to do a decision tree regression. In decision tree regression, the motivation is can we improve on the prediction of the fourth cut, because fourth cut was only 54%. So if I try with level 4, level is equal to 4 in case of decision tree, I get a r square. I get a much better r square. So decision tree is working better with the fourth cut. Now let us have this comparison for all the cuts, and what I find is in most of the cases, in most of the test cases, this works good. I mean, decision tree is almost everywhere uh, beating the standard normal linear regression hands down. So in order to improve the performance further, what we did was we tried a gradient boosted tree, and the results indeed were better in this. And finally, we have a comparative evaluation of all the three models here, and as you can see, much better prediction. It is weak on cut 5 and 1, but still better than others. So coming back to the presentation, I showed you the visualizations, which first of all the uh, this heat map, and then the individual pairwise combinations, and then uh, If you look it here, then the feature engineering part, and finally what we just went through was the model and the evaluation. So we stopped here basically because in this toy project we didn't come up with a final data product, but our final data product looked like this. It was a shiny platform in which I was allowing the user to select the different ranges for the components, and I was predicting uh, the output. So the possible limitations are we do not have the actual test data from the lab, and for in order to see whether how well the model is working, we'll have to wait for a year till the next assay is produced. So model will be slow to mature, and a vision I can say is probably of a mature product will probably be in the form of a mobile app which the refiner will be able to use to immediately find out what is going to be his yield in the product, and so that he can make the appropriate tuning. One thing I forgot to mention, it is important to uh, know the individual components, because refiners often say that I know what is going to be my cut if I know that the where the crude is coming from. But many a times it so happens that the crude is kept in a place such that two crudes gets mixed together. So then this the properties of the mixture, how it will determine the individual cuts, it becomes an interesting question. So that's it. I mean, this model probably will be enabler in that aspect, and probably it will be helping refiners to better leverage their uh, better leverage the performance factors which they have found. So that's it. Thank you.